Welcome to meeting number 10 of the M2D2 series. Today we are very much excited to have Wengong Jin with us and to present his work on iterative refinement graph neural network for antibodies, sequence, and structured co-design. A bit more about the speaker before we start. Wengong is a postdoctoral fellow at Eric and Wendy Schmidt Center of Broad Institute. He finished his PhD at MIT under the supervision of Regina Basile and Tommy Giacola. His research seeks to develop novel machine learning algorithms for biology, including drug discovery, immunology, genetic engineering, and synthetic biology. He is particularly interested in deep generative models, graph neural network, and geometric deep learning. Thank you so much again, Wengong, for accepting our invite. And yeah, the floor is yours. Looking forward to your presentation.
Cool. Thank you for the warm introduction. So today I would like to talk about our recent work on antibody design. This work is done with Jeremy, Regina, and Tommy, and it's in ICLR 2022 this year. And so let's get started. So just a kind of a quick introduction to what therapeutic antibody is. I guess everyone is kind of familiar now because of the COVID, right? You all get like antibody test or something. But basically antibody, binds to like antigens, like for example, like viruses, or it could be something else like cancer proteins or etc. And tries to block their function. Or in the case of virus, you want to block its infection, right? So this is kind of a figure of some antibodies binds to this green stuff, which is the virus or antigen to be more specific, and then tries to block its function. Its therapeutic utility is usually determined by the binding affinity to an antigen. So basically, you can see on the right-hand side that some of the antibodies can fit right in, some of them could not, and that has like a huge difference in binding affinity. So kind of, I know this is a little bit kind of just into a little bit detail of what antibodies are. So antibody, it has two chains. One is the heavy chain and the other is the light chain. And it looks like this Y-shaped thing, so it usually have the two kind of tips, right? That's where you actually bind to the virus or antigen. And if you zoom into this tip, right, this top part, it looks kind of like this. This is the cartoon version of it. It has like several parts, right? So it has the one part is called complementarity-determining region, which this part has around like 10 to 20 residues. Each residue is basically a circle here, and each capital letter represents a amino acid, and you have a bunch of residues here in the CDR that are hyper variable. So they have a lot of variability, and the rest part is kind of called framework region. It has relatively lower variability, and this CDR part is so each antibody has like 3 CDRs on each chain, and they are the major like players in determining what binding affinity is. So given that the field of computational antibody design, of course, the goal is to design these high affinity antigen binders or neutralizers. What neutralizer basically means to block, not only bind to the antigen, but also blocking its function, right? So a little bit better, doing something a bit extra than the binder. And again, this is similar to the story of small molecules. You have antibodies, and they all associated with properties. In this case, we are particularly interested in binding or neutralization, but also like other properties like stability, etc. So again, there are two directions of this problem, right? So we want to, given an antibody, we want to predict whether we can predict its binding affinity given this antibody structure. or sequence. And the other direction is, going from the property, can we generate some sort of antibodies with high binding affinity? So, and the antibody design community mostly focuses on this CDR design because the other parts, they don't vary that much. And also it doesn't really interact with the antigen closely. But even just for this CDR part, it's already challenging enough, right? So you talk about this antibody has like more than 100 residues, but the CDR part still has like 10 to 20 or 30 residues. And each, because there are 20 different amino acid types, you can easily go up to 20 to the n, right? It grows, the search space grows exponentially. So a quick question on like, what do I mean by stability and binding? Binding basically means, wait here. So binding basically means how good it kind of sticks to this antigen. And if you can stick to this antigen well, then you will not fall off, right? Then it could stimulate immune response much better. If you cannot stick to this very well, then you cannot tag this. Basically, an antibody is a tagger that they tag these bad stuff. Stability is more or less like, let's see. Stability is mostly like you will not degrade. So some of the antibodies, they may fall apart if your structure is kind of unstable, right? So it may fall apart, it may not fold in the right shape, then you get into trouble. So that's sort of a quick clarification. By the way, if you have quick questions, you can either put it into the chat, or if you want immediate attention, you can raise your hand as well. Cool. So, this is not a new problem, right? There has been, a lot of people are trying to kind of tackle this problem on using, initially it's, or the existing approach actually, it builds on this physics-based model. And the famous example is Rosetta, which is a super versatile and powerful tool. It basically goes into this kind of workflow. It has this heavy chain and light chain of the existing antibody, and it tries to redesign the CDRs. So that's basically you take out the CDRs, and then you go through some database, and then you kind of took some canonical CDR structures and graphed it in, and then you do some energy minimization based on this physical force field, and you try to find these good CDRs that kind of has low energy, so which means kind of stable, right? Well, this problem is not using this framework is good, but it is very computationally expensive, and it can take more than 10 hours per instance. And if you want to kind of do this optimization for many sequences, then you get into trouble. So what we have been thinking about is, can we use AI or machine learning to kind of do this in a much faster and better way? Of course, this is a moonshot, right? By no means that I can solve this just within this talk, but I just want to kind of illustrate some of the ideas and kind of introduce the field and move this forward, right? So this is kind of similar to small molecules again, right? So, but just to follow what Rosetta is doing, right? Well, now what I can do is, first, instead of going through some database search, I can use generative models to fill in these CDRs. And in terms of this energy function, right, I can, for example, if I care about neutralization of this antibody, then I can use some sort of neutralization predictor, which can be built on existing binding or neutralization data, and use that as basically a model-based design. Use this as sort of a reward function. Then you can go through, or you can do some sort of Bayesian optimization. So basically, the generative model's objective is to maximize the predicted binding or neutralization improvement over the existing antibody. So that's sort of the basic idea. And let me go through. So today's talk will have kind of 3 parts, kind of gradually unraveling the different components of the method. I think the core is the generation architecture. The other 2 are relatively more straightforward. But let's talk about how do we generate the CDRs. This problem, if you just view each CDR as a sequence, right? You can always take so for whatever protein, you can always view it as a sequence, right? A sequence of amino acid tokens. Basically, here for this CDR, the sequence will be ARGDY, blah, blah. Okay. And you can use, say, recurrent neural networks to generate these CDR sequences. And this is, I wouldn't say this is a bad idea, right? It can generate reasonable CDR sequences. But if you want to kind of push this a little bit further, then you will see actually this has some limitations. And the major limitation is it does not really take into account the 3D structures. And why does it bother? Well, as I kind of mentioned earlier, this binding affinity, I always talk about matching, right? Shape matching. Basically, some antibodies, it matches the shape of this antigen, then it binds this well, or some other things that it doesn't bind well because the shape is kind of bad. So we want to take into account the shape while doing generation. And that's sort of the core sort of motivation of the method. And I will not talk too much about sort of the background of general protein design. There are actually various ways of formulating how to model the relationship between the sequence and structure. Actually, many papers, many methods actually assumes the 3D structure is given and kind of generate the sequence given that structure, which is called inverse folding. This is not the approach that we're going to take because we don't think that assuming a given 3D structure is a reasonable assumption during design. So rather, we formulate this as a joint generative modeling problem, basically having a generated model and generate the sequence and its structure simultaneously. And that's sort of the major difference between our method and the previous protein design work. That's actually an interesting idea. Can we kind of generate this simultaneously, right? So in order to do this, we need a compact representation of this sequence plus structure thing, right? This object, and we can kind of represent this as a geometric graph. Basically, you have a bunch of residues here. These are the nodes, right? And then you have you can say if you know what's the true like 3D structure you want to generate, then you can construct a k-nearest neighbor graph out of it. And each edge has some features like the distance or even orientations between the 2 residues. I will not go into too much detail. You can go through in the paper. Okay, so now the question is, how can we generate this geometric graph, right? So we can, graph generation is a okay, yeah, I have a question. Yeah, I saw this comment. Binding does not always imply neutralization. So is there any other benefit taking into account 3D besides binding? I think neutralization actually depends more on the 3D structure. So binding would just first of all, you have to bind in order to neutralize, I think. And I remember a couple of papers actually more on the biology side that kind of says that you need a particular pose in order to neutralize well. Cool. So let me talk about how do we generate this geometric graph. Okay. This graph generation has been a very hot topic these days, especially in like small molecules or biology, right? So that's where so a standard sort of approach of generating these graphs is autoregressive models, right? I know that there are a lot of works these days in tackling the problem in different approach. But if you just look at these standard autoregressive models, it will say that I will say that this is not really suited for this geometric graph generation. Basically, if you generate things, right, this one by one, right, if I add residues one by one and then kind of figure out what are the edges in between, you will see that the things that has been generated before will be fixed, right? The history will not be changed, right? You cannot change history. But if you kind of think about this from a physics point of view, when you kind of, magically insert a residue into this protein or antibody, then you would imagine that the previous residues would change because of, say, physical forces. This is kind of just a mind experiment. Just like I don't think you can really insert residues in real antibodies, but you would ideally want to have some sort of thing that can kind of everything can change on the fly, right? So I think there are many different approaches to achieve this goal. We kind of looked at a very simple way of achieving this goal, which is called iterative graph refinement. So basically what we're looking at is, the model can still generate amino acid sequences autoregressively, right? Because the this sequence component is discrete. So in a way that it's not that easy to kind of modify it on the fly. But we can kind of modify the structure of this, we can modify the 3D structure while we are generating the residues. And what we can do particularly is we can, at each generation step, we can kind of update the pairwise distances between all residues, including the one that has not been generated. So this requires us to kind of predict how many residues are there in the beginning, but this is not too difficult. If you have basically, if you know how many residues are there, then at each step you basically kind of try to morph that shape. And based on the new. So every time when you insert something new, you will try to adjust the global structure, including the future residues. And this it's not a complicated idea. What we can do is just go into a little bit of detail of how to implement this, right? We can go, encode this CDR graph, right, using whatever neural network that you want. And you get this encoding, this hidden state of this new residue. This is the residue that we want to generate. So we go through this. If we make this prediction, we put this in, say this residue should be amino acid Y, right? You can sample this during training. You can just do teacher forcing, and during testing, you can just sample it from this softmax distribution. Then we would, after we get this new information, we try to update this structure, right? You see that the shape kind of morphs a little bit. And what we do is we predict the C alpha, basically the alpha carbon coordinate of each residue, not just Y, but everyone. And you get the different coordinate and you get different shape. You might immediately ask, if you just predict the coordinate, it doesn't seem rotational translation invariant, but this is not, but as long as you're actually, if your loss function is just operating on the distance, then actually you're good, even though I'm predicting the distance. So this distance will kind of just be some sort of, coordinate system that model kind of just chooses internally. And the whole thing is still rotation translation invariant. So, and you do this, you calculate this distance logs at every step. So that's sort of the idea. And I can go through for the next residue and again, get the new coordinates and do the same thing. So let's take a look at some results. Basically, we want to kind of ask two questions. One is if the generated CDR structure is correct. And again, right, we have baseline, which is just autoregressively generates these distances, but fixing everything, fixing the history, right? There's no refinement. And you can see that I should have mentioned that the data set is come from this structural antibody database. It's a subset of PEB, but only antibodies. And we split the training and test set based on the CDR sequence similarity, because we want to make sure that the test set has decent, divergence from the training. We don't want to have just tests on CDRs with almost the same amino acid sequence as some of the thing in the training set. Okay, so the metric is root mean square deviation. Basically, you can see this on the right? Basically, it kind of calculates what's the deviation between the two, between each atom. And okay, how do I initialize the coordinate at the start of optimization? Okay, that's a great question. We kind of just initialize it as a chain. That's the initial position of each residue. So, okay, cool. So you can see that this iterative refinement kind of gives you a lot better RMSD compared to this autoregressive generation. And if you just kind of give you some example of how these two things differ, you can see that this sequential generation, these autoregressive ones, will generate something a little bit weird because it does not allow you to fix the errors that you made in the past, right? So this refinement thing could kind of fit better. Of course, there are failure cases for iterative refinement as well, but overall, it does much better than this sequential generation. So now the other evaluation is on log likelihood. So, well, because we are dealing with generating sequence, right? So it is similar to language modeling, and we can always calculate perplexity, basically the basically log likelihood. Okay, so we can compare with say sequence-based models and also this autoregressive graph generation, and we can also do much better in terms of perplexity. And I think an interesting kind of result is if let's say I know the ground truth 3D structure, how far we can go if we know the 3D structure, and this gives you perplexity around 7. So basically, you can see that okay, this blue bar is totally agnostic, right? It has no structure involved at all. This orange one is knowing the ground truth, using the oracle, and you can see that our model kind of goes in between. So it seems like it's utilizing the structure in a decent manner. Okay, so at least much better than this autoregressive generation component. So that's sort of the take-home message. Okay, so now we can kind of, after we have talked about this generation, right? This CDR part, we still need to kind of look into how can we generate these CDRs that are compatible with the given framework, right? And this is an important question because if we do this sort of, this is more like antibody optimization, right? We want to kind of modify the CDRs to improve their neutralization. And you want to kind of put in stuff that is compatible with the existing frameworks. So here, we need to do some extra work. So how do we kind of do this conditioning, right? Basically, it's now conditioning on the CDR generation. Okay, I just also saw another question. The loss is also reflection invariant. Does this not negatively influence the results? I agree. I think that's a good question. So perhaps what we can do is to use some sort of like, for example, in AlphaFold, we have this FAPE loss. Maybe we can use that. That is reflection, that is sensitive to, that is not reflection invariant. which it's a good kind of thing to try. Because our model actually also, I didn't talk into too much detail, but we also predict the backbone, other backbone atoms like the carbon and the nitrogen. So we can actually construct that frame on the fly, and then use that frame to do the FAP loss. That's a good question. Thank you. So okay, now coming back to this, framework conditional generation. Basically, now, okay, I'm not just looking at the CDRs, right? But I also want to kind of take into account the information in this framework sequence. So framework, just to remind you again, the framework is the one that supports the CDRs. Okay, now we can do is, okay, this framework sequence, it is known, right? But we only know that the sequence. Let's see, I saw just another question. Let me leave it to the end because it will take a little bit of time. Okay, so now here, coming back, what we can do is we can encode this framework sequence using some recurrent neural network, right? This is nothing, there's nothing fancy here. And then we can use some sort of attention. So basically, kind of, it's like a sequence to sequence, but or sequence to structure, that you encode this framework sequence with some recurrent neural network and use some neural attention in between. But this does not kind of model the sequence CDR compatibility in the best way, because as you can see, right, these CDRs already are described by this structure. But the framework is kind of something that's ad hoc editing using some attention. It doesn't seem as a clean and nice story. And also, we do want to kind of model this CDR framework compatibility also at the structure level, right? So we want to kind of look at this, kind of have a more unified way of modeling the sequence and the framework and the CDR in a coherent representation. So the immediate thought is we can extend the graph representation, right? We don't have to kind of just you formulate CDR as a graph and the rest as sequence, but rather taking the whole thing as a graph, right? Basically now we need to each edge would connect two residues in both CDR and the framework. And you have, each edge has some sort of distance or orientation features between the CDR residues or between a CDR residue and a framework residue. And this joint graph representation characterizes sort of the 3D relationship between the CDR and the framework in a nice way. So, and we can just run a graph neural network on top of all this, and it's a much nicer way of characterizing the whole thing, right? So this is more like a graph completion, right? You have some, well, by the way, we don't really know what's the 3D structure of the framework either. So we actually need to figure out what are these distances. So these needs to be predicted, and that's when so that's why we need to actually use iterative refinement over the whole thing, right? Not just at the CDRs. Even though we are generating the residues in the CDR region, but we need to predict the 3D coordinate of the framework residues and the CDR residues at the same time, in order to kind of generate this framework CDR graph at the same nicely. So this is the same, right? As before, you just extend this refinement and also the graph neural network encoding to the framework region. There's a little bit of caveat, is maybe we, well, because the framework plus CDR contains too many residues. It has like 100-ish. And you don't want to kind of run graph convolution over the whole thing in every generation step. So here's a little bit of a trick or hack into accelerate this whole process. We basically kind of coarsen the framework region into formers or into k-mers. Basically, if k equals to 4, then you take so at the framework, each block contains 4 residues. If you take k equals to 8, this block will have 8 residues. So because frameworks are relatively static, so we thought like, okay, this thing would be some would not lose too much of granularity, right? And now in total, if k equals to 8, you basically have framework around like 13 blocks, and then plus another 13, another 15 to 20-ish residues in the CDR, and then this is a manageable size to do this iterative refinement thing. So that's sort of the idea. And okay, just one little bit of detail. Okay, so how for each block, right? The initial embedding of this block is basically the average embedding of each residue. Basically, take the so we have an embedding layer that represents each amino acid, and you can just take the average embedding as the initial embedding of this block. The true coordinate of this block is basically the average embedding of the average coordinate, basically the mean of these 4 residues. And now what we do is, okay, I can do the same iterative refinement thing, right? This is the same figure, just kind of merge the 2 steps into one figure. And now the loss function is operating on the true distance that's calculated based on the, so the distance between the 2 blocks is basically the distance between their mean. So that's what I wanted to clarify. Cool. So I think this is sort of the second part of the story. Let's look at some of the results. Again, right? So all these baselines plus the result is actually already using the framework, even though I didn't talk about it in the first part. So if we do not incorporate, if we just use attention to condition on the framework sequence, then you get slightly worse perplexity. It's not like significantly worse, but has some small has some decent degradation. If you just not condition on the framework at all, you basically, if you just generate a CDR without using the framework, they will give you 8.95. So the baselines are already using the framework. So the first 3 rows are compatible, that just to clarify. And so basically the take-home message is using sequence level attention is not good enough to model the CDR framework relationship. That's an interesting finding. So another experiment that we did is we want to kind of compare with Rosetta, just to see if we can do much faster. This whole thing just takes you can do like 1 second per sequence compared to like 10 hours per sequence for Rosetta. But can we do better in terms of performance, or are we actually losing a lot of performance? So here we take the benchmark data set in Rosetta antibody design. They have they have around 60 antibody antigen complexes that they have chosen, and their evaluation metric is called sequence recovery. It's, to be honest, it's about the same as perplexity. It just is a more it's not taking into account the probability, but basically you just generate CDR and then compare like how many residues actually match the ground truth, and basically the lower perplexity, the higher this thing is. So you can see on the left-hand side, on the right-hand side, this Rosetta has around 28% sequence recovery. Our model can do better while also being faster. So this means that we can kind of do this computational antibody design in a faster and better way. I think this is promising result. And okay, the last part that I want to talk about, which is relatively shorter, is CDR optimization. Kind of now, okay, the first two parts are just looking at the generative modeling part, right? But if you want to complete the whole story, if we want to use this neutralization predictor to kind of generate something to guide the design, we can, this is not a new problem, right? You can use model. It's basically called model-based design, and you can use. There are many methods already, like reinforcement learning or like some sort of EM algorithm on top. There are many ways to do this, but basically, the optimization objective is to maximize the expected neutralization score of a generated antibody. And if you can do this, then you can automatically design things that not only binds, but also neutralizes. So here, we are interested in this oh yeah, any clue why you can do better since Rosetta uses the full 3D structure of the antibody? I think it's basically that you are, how can I say? I would say that it's because the optimization, this energy function is quite hard to optimize. And it's just really easy to stick into like local minima. I'm not sure. This is a great question. We ran this, and we also seen the same story in like Rosetta, let's say fixed backbone design. That's in some other papers, like when they do like protein design, they also see that generative model can do better than Rosetta in like general protein design. So it seems, I don't know, like I'm not like that. I'm not the expert of Rosetta, so I'm not sure if I can answer this question in the best way. Okay, cool. So here we are interested in a specific task in SARS-CoV-2. We want to kind of design neutralizing antibodies against SARS-CoV-2, and here we used existing sort of neutralization data from this coronavirus antibody database. It's constructed by Oxford University, and it is a growing library. So it has already the database is growing actually rapidly. It has already around like 5,000 antibodies with measured neutralization against. Right now, it's not only just the wild type of, but also some variants like alpha, beta, or like kappa. Omicron even. So it's an interesting database. We took the data of basically each antibody and a spike protein sequence, the RBD, the receptor binding motif, the receptor binding domain. And we trained a sequence-based classifier, basically classify whether this antibody neutralizes the COVID virus. So this is not, and there's nothing like complicated here. We use that as a, as the model here. Basically, use the predicted neutralization score to guide the generative model in the CDR design. But we want to kind of just mention. I want to mention that there's additional constraints. It's not just about maximizing that neutralization predictor score. There are some other constraints. I would point you to this paper, which has carefully sort of thought about how to do what makes the antibody developable, basically can put into clinic, right? So there are some additional constraints. They wanted kind of to follow the Lipinski like rule of 5. So they also came up with 5 computational rules. Unfortunately, many of the rules actually requires that you know like the real 3D structure. But here I just took a couple of constraints that are easy to evaluate, even just at the sequence level. Basically, for example, the hydrophobic, you shouldn't have too much like hydrophobic residues clustered together, or you don't want to like having the CDR residues having a lot of charges. And you also want to avoid some like glycosylation motifs. These are more like into biology, so I won't go into too much detail of these constraints. We can also kind of constrain the perplexity of the generated CDR sequences, so that the model will not generate these weird CDR sequences. And I think that these additional constraints is important for this this whole like model-based antibody design framework, right? So that you will generate things that that can be put into experiments, wet labs to actually test. So this is sort of the idea. It's not like super complicated. Oh, I actually had an illustration here. Basically, now in this generation, in this optimization framework, I will reject any sequence that has lower neutralization than the original one, or violates charge or perplexity constraints, right? So that's sort of the basic story of this antibody optimization framework. And we did experiment on this SARS-CoV-2 neutralizer design. I just want to say that this is a little bit this is synthetic, because we use this trained neutralization predictor to evaluate how good an antibody is. So this is just for like in silico experiments, just to see whether if you have a better generated model, does it help this multi-objective optimization task? But I would suggest that you should look at this after we done, say, like in vitro experiment, and see if this actually holds, right? This is the real evaluation that we should take. But nevertheless, it's still helpful just to look at this figure. And you can see that this refinement-based generated model also does better in terms of this multi-objective optimization. And here is some examples of some antibodies in this coronavirus database. It has you can improve, you can replace the old CDR with this generated CDR, and you can improve the neutralization score by well, basically this is the probability, and you can improve the score better. So kind of I think it's kind of already around the clock. I just want to kind of conclude and also take some questions. But basically, in the first part, we talked about this generated model, and we wanted to actually do sequence structure co-design. And we use iterative refinement way of generating this joint object, this sequence and structure. The second part wanted to what is the problem, right? Is trying to kind of make sure that your generated CDR is compatible with the framework. So we extended this graph representation to include the frameworks, and also using some post-graining to do the acceleration. And the third part is kind of looking at model-based multi-objective optimization of this antibody design task. And that's sort of the whole. This is the end of the talk. I want to just thank. There are a lot of collaborators and a lot of people supported this work, and the code is online, so you can kind of look at it and play with it. Cool. I think we can. I can just end. Okay. Yeah. I can take some questions, and there are already some questions in the chat. What's the percentage of generated CDRs that violate the constraints? That's a great question. I actually forgot. I need to look at it. Sorry about that, but I think it's. Let's see. So I remember like the model, it's really easy for a model to kind of generate a lot of charges. So the reason why we incorporated this developability constraint is, we have some collaboration with some biologists on like designing antibodies. So we had some initial, build this model, and we design, generate a bunch of sequences that has high like neutralization score predicted by this neutralization predictor. And the biologist basically said, oh, that's a lot of charges. So it doesn't seem like it's doable. So we, I think that's without any of these constraints, right? So I think without the constraints, the model will generate a lot of charges, seems like. Another question, since you run message passing over all the nodes in the graph, why is it necessary to generate residues one at a time? Yeah, that's a great question. I think we tried a couple of variants, like we generate, say, 2 residues or 4 residues, and then like do this structure refinement. I think it did slightly worse, but it's quite similar in terms of performance. So again, there's no reason not to kind of well, okay, I should say that the reason we did this autoregressive sequence generation is actually for the sake of evaluation. We wanted to actually calculate perplexity, and that actually constrained the way that basically, if I don't do this one-by-one generation, it's not easy to calculate the log likelihood. But I would say if we can come up with some better way of evaluating the generated sequences, then we don't have to like generate this one by one, but also like generate everything like at the same time, maybe just not autoregressive, that would be also fine. Yeah, so again, right, these are not necessarily the best way of doing this. For example, I saw that in the chat that you can generate the CDR residues based on like whether it is based on the confidence. Yeah, sure. I think this is maybe we should kind of think carefully what is the confidence that how to evaluate the confidence, but kind of go through, say, like easy first generation. Like if this position is easier to decide, then we can generate this residue first, or something like that. That's so again, right? This I just want to say that this is totally open area that a lot of formulations, and you can do this. It doesn't have to be the way that I have done it. Another question is, what's the theoretical explanation why GNN-based methods guaranteed outperform VAE-based methods? Oh, I mean, VAE is not, it's orthogonal, I would say. That VAE is a way of, formulating this probabilistic generated model. VAE can be used with GNN at the same time. So that's totally not the issue. So for example, our work can also use VAE, right? Basically having a sort of prior distribution and then sample some noise Z from this prior, and then generate, well, basically we can have an encoder and a decoder, and we can encode this true antibody plus structure into some latent representation, and then reconstruct the thing from that latent representation using iterative refinement or whatever. That's totally fine. So basically VAE can be combined with GNN. I remember this on a previous question on from Emmanuel. What is the was the reconstruction of all structure similar in accuracy? So CDR loop is a loop, and so everything is loop. There's no beta sheet or helix. But it will be curious to see if we apply this for some other secondary structure, how does that do? That's sort of the, yeah, basically loop is one type of secondary structure. It is different from alpha-Felix or beta sheets. So we are kind of just looking at the loop for now. Right. Okay.
I have
Any questions that I missed? Does your proposed algorithm outperform DeepMind's AlphaFold? That's a really good question. We are, I think we should run it. That's something that we are looking at, but not in terms of just the CDR loop, but also want to see that if, well, so, okay, so there are some differences because we are kind of generating and also folding at the same time, but we are just folding that CDR part. DeepMind's AlphaFold will fold the whole thing. So I wouldn't say that, even say that our model can do better in the CDR loop. I don't think that our model can compare with AlphaFold because AlphaFold will fold the whole thing, right? So it does much extra job. Our work kind of focuses on the generation side, kind of wanted to incorporate structure as much as possible. But I think that's a great point. I'm actually doing some analysis now, but kind of setting up the AlphaFold and then running it. Maybe once I have the result, I can kind of share it in the paper once if it is once it's ready. It runs really slowly, so we will see. But again, right, I don't think that the two methods are really comparable in a way that AlphaFold does much better, much extra job, right, folding the whole structure of the framework plus the CDRs, while we are actually generating while folding. So we need to actually fold the partial sequence, basically. So that actually has it's actually harder. Like imagine that you have some empty sequences and some generated sequences, and you want to guess the structure. So that's a little bit hard. Anyway, do you compare with this approach with the approach where you refine the whole structure only after generating all residues? So that's a good question. I think so another way of looking at this is I can just generate a sequence and then kind of fold it whatever way you want. This would not, this would basically give you the same perplexity as the sequence-based model because you are not utilizing the structure while generation. You can of course get the structure after you have designed the sequence, but you are not utilizing the information on the fly. So that kind of, you basically use a, you generate a sequence without knowing the structure or without kind of guessing the structure. And that gives you poor performance compared to like looping the structure in during the design. Yeah, I think this is the answer to the question. So, I have
one question. So when you have multiple CDR in your antibody, how do you go about the optimization? Do you design each of them sequentially? All of them?
Oh yeah, that's right. That's a great question. So I only, in the whole talk, I'm only just, for the simplicity, I just showed I'm designing one CDR, but you can design the 6 CDR sequentially. That's the way that, well, just to clarify, in the experiment, in the paper, we didn't do that. We just designed the CDR3 of the heavy chain in this SARS-CoV-2 neutralizer design. But we can do this, you know, you can start from CDR1, CDR2, and CDR3. So that's not a problem. Yeah.
Okay. From my understanding, the CDR kind of interact with each other, right, in the 3D space.
Yes.
So then how do you take into account those interactions? Like, because if you design one and then go about the second one, then the first structure is phased while you're designing the other one. So
yeah, great question. So let me pull up a figure, right? So basically, what we can do is, I will just take a simpler one. So that's a great point, right? So when I said that you can design this sequentially, it's not, you can do this iterative refinement on the 3 CDR at the same time, right? Because there's no restriction on like just designing 1 CDR at a time. You design the 3 CDR at the same time. So, but you still generate the residues kind of one by one, starting from CDR1 and then go to CDR2 and CDR3. But the structure, it's actually iterative refinement over the all the 3 CDRs. We haven't tried like doing the heavy chain, light chain at the same time. But I think it's in principle it's the same. Actually, in the GitHub, we have actually code that does 3 CDR design at the same time. So that's not a big deal. In implementation, it's the same. Having 3 CDR or 1 CDR is the same. So still the same graph representation. It's just no longer just 1 loop, but 3 loops, kind of, right.
Cool. Any more questions from the audience?
I see another in the chat. Do you need to measure the validity of the generated CDRs? So a little bit different from small molecules. To be honest, like every CDR residue should be valid in a way that you can, in principle, engineer that and produce that CDR sequence, with the antibody, of course. But some of them do not fold nicely; they break. So that's why I mentioned that in the case of these proteins, the validity is really the stability, which is not easy to quantify, to be honest. So you can see that for example, this paper tries to kind of at least extract some information from the clinical like therapeutic antibodies, just to see that what are the good criteria, right? This similar to the drug likeness, the rule of 5. They calculate this rule of 5 based on some hydrophobicity or like charges, something like that, right? So these are still like empirical. Like it's not like ideally you want to kind of have a way. Maybe you can run an assay to measure the stability and then kind of use that to measure the validity of the CDRs. So that would be the best way, but it's definitely it would require you do wet labs, so it's not that feasible. Another last question: have you thought about doing batch refinement, updating structure only after a few generation steps? Yes, yeah, you can actually do that. We tried that. The performance is relatively similar. I only tried like 2. So that's something that I only realized at the end, like after we have done all these like coarse graining and a bunch of stuff. So, but for sure. So there are other ways to kind of reduce the computational cost. Doing this batch refinement is also a good idea.